Hello, my dear students, and welcome again in the Informatics 2 class. And this time we're going to start a very interesting topic, which is stacks. We're going to talk about stacks in this lesson, lesson number 11, and in the common lesson as well. What are stacks? That's the first thing we're going to talk about. Stacks in our life. And then, what are stacks in the computer terminology? So we're going to define stacks according to the computers, and then based on that, we're going to see how we're going to manipulate stacks, of course, computer stacks this time. And then we're going to define the very basic operations performed on stacks. And then after that, we're going to implement these operations using first array implementation. Of course, there are other implementations, and we're going to talk about these other implementations as we move on with our classes. Okay, let's start from stacks in our life. Well, everywhere. Stacks are basically everywhere. If you go to the cafeteria, you go to grab a tray, and you will find a stack of trays in there, a bunch of them. At home, you collect coins. Okay, and you make a stack of these coins on top of each other, like that. In your closet, you're going to have a bunch of boxes stacked on top of each other, like this. Or in your clothes cabinet, you're going to have, maybe you, maybe your mom, cleaning your shirts, stacking them on top of each other on one of the shelves there. So basically, you might think of anything to where you would like to put many things on top of each other's, like this, books on top of each other's. This is basically a stack. This group of papers in here, on top of each other's, basically they're a stack. So stacks then, in our real life, they go everywhere, anywhere, as a matter of fact. And we always would like to access these stacks. I would like to grab a tray from here. I would like to grab a shirt, to grab a box of one of these, and so forth. Well, do we have similar thing in computers? Do we have stacks in computers? Yes, of course, we do. We have a bunch of data in there. It's not shirts, not trays, but rather objects, or elements, or structures. So somehow we're going to stack these structures, these objects, on top of each other. So I will have some sort of a container like this in my computer memory, and in this container, I'm going to have like objects on top of each other. So a stack is a data structure in which all insertions and deletions of entries are made at one end, called the top of stack. So when I have these then objects stacked together on top of each other, then I cannot access this very last one. Of course I can, but I'm going to destroy all the rest of the trays. Typically when you go to the cafeteria, you're not going to go to the tray at the very end of the stack, but rather you're going to grab one from the top. Hopefully you're going to grab the top shirt to wear it. Otherwise you're going to make a mess. And that's how we always actually access stacks. We always go to the entry or the element or the object on top of the stack. So we always go to what's so-called top of stack for accessing the stacks in computers. So that means the accessing of this type of structure is not actually random, in a sense that you don't go anywhere you like and access the object you like right away, the way we used to when we were talking about arrays, when we were talking about random access memory, to where you can go to any location at any time you like. Rather, in stacks, you always access the last entry on top of the stack. The last entry you put on top of the stack is the first entry you take out of that stack. That means the last item that is put onto a stack is always the first item that you will take off the stack for processing. This is called, in computer terms, LIFO. Last in, first out. Okay, so this is a very well-known policy in accessing items. LIFO. So stacks are LIFO. Okay, what kind of operations I can perform on a stack now once I know what is the basic structure of the stack? Well, I can always, the very basic thing, I want to add items to my stack. This kind of operation to where I add an item on top of the stack is called push. So you push an item to your stack. That means you add an item to your stack. Where does it go? It goes on top of the stack as a very last entry in my stack. Well, there is a possibility of an overflow. When does this thing happen? Well, if it happens, if my stack is really full, if the space I'm allocating for my stack is actually exhausted, it has been filled with items, and you're attempting to put a new item and there's no room for it simply. We call this in computer terms overflow. What else we can do on a stack? Well, definitely the same way I put items, I would like sometimes to retrieve items from the stack, to take items off the stack for processing. Okay? This kind of operation is called pop. So popping from the stack is basically taking items off the stack. Of course, the item I'm going to take off the stack is definitely the one on top of the stack, the very last entry that I have already pushed a little while ago. So pop means remove an item from a stack. Well, what could happen if I attempt to retrieve an item from an empty stack? Well, there's nothing in there and you're trying to retrieve something. I don't have anything to give you. This is simply called underflow. Okay? So basically in a picture, pushing to the stack means putting items on top of the stack. Popping items from the stack means basically taking items or retrieving items off the stack. So this, the push, increases the size or the number of elements I have in the stack, to whereas popping from the stack leaves the size of the stack shorter or less. Let's look at some illustrations in here. Assume that this container is actually my stack. I just started with this container, so I don't have anything in the stack. It's empty now. I don't have any items in there. And now I would like to push an item to the stack. This disk in here, named Q, okay, is needed to be pushed to the stack. So I send it there. As a result, I have one item now in this stack. And it's the very last item I have. So in terms of computers, I have a pointer that points here, indicating that Q is the last item I have in my stack. Okay? Here is another example. The same Q, but now it has already the item Q, and I would like to add more items. This disk here, called A, I would like to push it to the stack. Well, pushing this to the stack means basically that I'm going to end up with a stack like this, 2 disks inside it, all right? And now the top of stack pointer is pointing here to this box, okay? Indicating that this is the last entry that I have in this stack. If I would like to pop now an entry, to retrieve an entry from the stack, then here's my stack. The item that I can retrieve right away in one shot is item A. So I can now retrieve A. And after this operation, I'm going to end up with a stack like this containing just one item, and my pointer is pointing now here. All right. Assume that I have an empty stack now, and I'm attempting to retrieve something from it. Well, there's nothing in there. What did we call this operation? Do you remember? Yes, exactly. It's an underflow. You're trying to retrieve information from an empty stack. This is basically an underflow. So anytime your stack pointer indicates that the stack container is empty and you're attempting to pop from the stack, okay, an overflow, an error occurs. This kind of error is called underflow. All right. In this scenario, my stack is full, and I'm trying to push something to the stack. Well, there's no room for it, I'm afraid. Well, what this kind of error? What is this kind of error? What did we call it? Attempting to push to a full stack where you don't have any room for the newcomer. Well, this is called overflow. An overflow is an error to where I attempt to add a new entry to my stack and the stack was full. Yes, this is an error, and I have to check for that always each time I try to add entries to the stack. Top of stack. Top of stack, as I said, it's always a pointer that always points to the last entry I have in stack. And that's the item actually I retrieve when I perform a pop operation. So I'm always going to have some sort of a pointer that points to the last entry in stack, and that means whenever you try to access the stack, to pop something from the stack, that's the candidate item actually you're going to retrieve. Of course, needless to say that if you would like to retrieve this box down here or this disk down here, then in terms of stacks, you have to pop all entries above that, okay? And then you're going to have access to this box. Okay? So accessing then stacks is always sequential rather than random, one after the other. And of course, the one you retrieve at the first time is the one you have on top of the stack. Excellent. Let's go to the implementation now of stacks in terms of programming, in terms of C programming. Well, before we start that, let's define some notation. Throughout our presentation in this class and the coming class, as a matter of fact, we shall use the following declarations. Stack is some defined type for stack. It's some sort of a structure, a container that's going to contain my stack. Maybe my stack is going to contain some sort of integers, then this is a list of integers. It could be structures, big, small structures, I don't know. It's a container. Okay, so I'm going to assume, just for simplicity, for the heck of this class, is that stack is already defined to be of some type, okay, and it's basically a container that's going to contain my entries after that. Well, how about my entries that I'm going to add to this stack? Well, I'm going to just call them stack entry. And again, stack entry is some predefined type for the entries that are stored in the stack. So the entries I'm going to insert in here could be integers, as I said, could be floats, could be structures, could be anything, okay? Just for simplicity, for the heck of illustration, we're just going to call it stack entry in general. All right, keeping this notation in mind, let's start by defining the prototypes of the functions that we can perform on a stack. The basic two operations that we define on the stack, as we said so far, is pushing something to the stack and popping some from the stack. However, there are many other basic operations that we need to know and perform on the stack. Let's see some of these basic operations. Let's start with the first function, which talks about initialization of the stack, to create and start a stack. Well, we're going to call this function create stack. That's basically to create a stack. The prototype for it would be something like this. It's going to be of type void. The name of the function is create stack. And we always, and this is a habit in C, and you have learned that in Informatics 1 class, in the C class, is that your names has to be logically meaningful names. So we're creating a stack, so why not calling it create stack? The argument I'm going to give, or the parameter I'm going to pass to this function, is a pointer to the stack S. And that's what I would like. I would like to create a stack called S. And S is actually a pointer to this container called stack. So it's a pointer of type stack. So the preconditions for this, inputs basically to this, and the assumptions before I get to this function, basically nothing. You don't have anything. And after you go through this function, you're going to have as a post condition, that's the outcome of this function, the stack is has been created and initialized to be empty. So as a result of this function, we're going to create an empty container like this called stack, called S, of course, of type stack, as I said. Okay? An empty container. All right? So that's basically what I would like to do in this operation. And I usually do this just once at the very beginning when I start my whole operation. Create the stack, and then you're going to work on that stack. Let's see how we're going to work on that stack. What other functions we can do? Well, sometimes I would like to check if the stack is empty or not. Well, because especially when I try to pop something from the stack, we encounter this problem of underflow. So basically, I think, and I'm thinking loudly now, is that before I try to retrieve anything from the stack, I would like to make sure, is there anything in the stack or no? Okay? So I need a function like this, which says yes or no, true or false, a Boolean function, basically. Okay? So the prototype for that is of type Boolean then. And Boolean means true or false. It takes one of the two values. And basically, the name of the function is stack empty. There is a space in here. Of course, that's obvious. Okay, stack empty, and it takes the stack pointer that we have for the stack. So I have a stack. Maybe it's full, it's empty, I don't know. A stack, and there's a pointer pointing to it called S. Okay? Pass that stack to this function. Okay? And this function is now going to check, is that stack empty? If true, return yes. Return true. Return 1. Okay? Otherwise, if there are entries inside it, return 0. False. Okay? So this is like a decision-making process I'm going to make later on in my program based on the result out of this function. So basically, the precondition for this, I'm assuming that the stack S already exists. It could be empty, it could be not, I don't know, but at least there is a stack called S. All right? And then you're going to pass this stack to this function. This function is going to check the stack, and as a post condition, it's going to return true, and that's 1 in terms of programming, if the stack is empty. Otherwise, it's going to return false, 0. Okay? So a yes means true, means 1 as a return value for this function. I could call it of type Boolean, or I could make it of type integer, and then I will return 1 or return 0, whether it's empty or non-empty as it goes. Okay, what else can we do? Well, I can sometimes check, and I would like, as a matter of fact, to check if the stack is full or not. And basically, I need this, as I said, when I attempt to push to the stack, to add entries to the stack. Then again, I'm assuming that a good programmer would like to check first before he adds any entries to the stack to see if there is any room for the newcomer or there isn't. So before I can push to the stack, I would like always to check to see if the stack is full or not. So pretty much this function checks an existing stack, okay, and it returns a Boolean value, a true or false kind of value, all right, indicating that the stack is full, right, or it's not full, so that I can add new entries or that I cannot just because the stack is full. So basically, the function is going to be stack full, that's the name of the function. Again, it's of type Boolean, and it takes as input a stack S. I'm assuming in here, as a precondition for this function, is that the stack S already exists. All right? I don't know how many items in there, but at least there is a stack called S. And then the outcome, or the post condition out of this function, is a true or false. A true if the stack is full, no room for any new entries, or otherwise false if the stack is not full yet and there is room inside it. Other operations, push. Okay, That's the very fundamental actually operation that I perform. One of the very fundamental at least. Push to where I add entries to the stack. Basically, this function is going to be of type void. It's not going to return anything. All it's going to do is to take an item of type stack entry, again predefined type as we said, and this item at the end of the day is going to be added on top of the stack S. Okay? So the precondition for this is that the stack S exists and this stack is not full. So before I can run this, I have to verify this condition by doing this, calling this function stack full, the one we just talked about a minute ago. So okay, two conditions then for this to have a successful result. First, the stack S exists and there is room inside the stack to put this new entry item inside it. As a result, the argument item is going to be stored on top of the stack. So the stack is something like this, and here's top of stack pointer. Okay, it's not empty, I still have room. So as a result, this new item is going to be inserted here, and top of stack is going to be adjusted to point to the last entry in here. Excuse me. Again, top stack was here, and I'm adding the new entry item on top, and I'm adjusting top of stack to point to this new item as it's the top of stack now. Okay, so the argument has been stored at top of stack. Other operations, pop from the stack, retrieve items from the stack. It pretty much works the opposite to push. Again, the name for this function, we're going to call it pop for short. Return void value. I have a stack already existing called S, all right? And this stack is not empty as a prerequisite. And then I'm going to take whatever on top of this stack, place it in item as a result of this function. So basically, the precondition for this function is that the stack S exists and it's not empty. Otherwise, I would have an overflow. So I better check that using the stack empty function first. Okay, and then as a post condition or the result of this, I'm gonna have the top of stack item removed from the top of stack, removed physically from the top of stack, and returned in this item. Okay, so as a result of this, I'm gonna have, if this was my stack, okay, and top of stack was pointing here. As a result of this pop, I'm gonna take this, put it in the container of the same data type as these, of course, called item. And then after this step, top of stack obviously is going to be pointing here. All right, other operations, clear stack. In many applications, I would like to flush the stack that I have. Forget all items, remove them all. I don't care about them anymore. And I want to start filling my stack again. I don't like the items in there for whatever reason. Okay? And that's very simple. All you need to do is to pop all of these, throw them away, and make your top of stack pointing to item 0 again, to the very first entry in there. Okay? And that way your stack is basically empty. So basically, the prototype for this is again of type void, and it says the name of it, clear stack, and it takes as an input the stack S. The only assumption in here is that stack exists and has been initialized. Okay? There is a stack called S, right? I don't know how many items in there, I don't care. No matter what, no matter how many items in there, I'm just gonna flush them, clear them, okay? Drop them. As the result of this, all entries are going to be removed from the stack, and the stack is empty, and top of stack is going to be pointing. I have so many items in there. I'm going to throw them away all together, and top of stack is going to go here. Okay? So that's the result of clear stack. I'm going through these prototypes just to let you know what kind of operations we're talking about in here. And then at the end of this class and the coming lesson as well, we're going to implement physically these functions all together. So please remember these prototypes as we move on. Okay. At some other applications, I might need to know how many items do I have in the stack. Yes, the stack as a container, I might know ahead of time that I could have in my cabinet like 10 boxes stacked together. But at any given moment, I don't know how many items, how many boxes I already have. Okay? And in some applications, I would like to know that number, how many items I do physically have. All right? For that, we're going to develop a function called size stack. And this size stack is of type integer. It's going to count basically the number of items in the stack. Okay? And basically, it's going to take as an input the stack is. So the only precondition for this is that this stack is created and has been already initialized. All right? And then, as a result of this, as a post condition for this function, I'm going to return the number of entries in the stack. Okay? Like 5, 6, 10 items in the stack already. Of course, I might use this for many applications, as I said. All right? Stack top, another function. Well, in many applications, I don't want to physically remove the item. Here's my stack, okay? And I have already some items inside it. And here's top of stack, pointing to the last entry in here, okay? I could pop this as we have seen earlier, okay? However, sometimes I don't want to pop it, okay? I just want to look at it to do something, and I want you just to keep it in there. I'm just going to look into it, and that's all. All right, and that depends, of course, upon the application we're talking about in here, okay? But this case exists in real life, all right? So in that case, I don't want to retrieve this top of stack item, but rather I just want to make a copy of it to here. Just copy it. Don't remove it, okay? And I'm going to be working on this item the way I like. But keep your stack unharmed, unchanged. Top of stack stays here. No change physically on the stack. What we're doing is just copying whatever item I have on top of stack to a new item outside the stack for further processing. Okay? So this is not popping from the stack, but rather copying from the stack. So it's slightly different from the pop, especially in terms of the top of stack pointer. So in this kind of function, stack top, nothing to return as a matter of fact, but rather I'm having in here item as a return value of type pointer. As a matter of fact, I should have an asterisk in here, a star in here. But anyway, I have stack is, which is already created, and it's not empty. It's like the case with the Bob. To make sure that I have entries actually to copy. And then as a result, I'm going to take whatever on top of this stack and copy it, make a copy of it in this item here, and just return. Leave your stack as is, unchanged. So the item at top of stack is copied, and I underline this word, copied into item. This is correct, and I should have it right here, okay? Without being removed. So it's copied to item without being removed, and the stack remain unchanged. Okay. Well, it depends upon the application, as I said. Sometimes I would like to traverse all entries in the stack and do something in there. Let's say the stack contains the records for the employees in my company. Okay, so each entry is actually a structure with the employee name, the employee ID, department he works in, and his salary plus other stuff. Okay, and I'm so generous, in a very generous mood, and I decided to give a raise $100 to everybody in there. So basically, I need to visit every record in the stack and change the contents of that record. We call this traversing the stack, okay? That means visiting every entry in the stack for processing, whatever kind of processing. Okay, so this kind of function, generally, it depends, of course, upon the way we're going to traverse it, but the way we can think of it is to return a value of type void. I'm going to call it traverse stack, and it takes as an input the stack itself, okay, and a function. And this function, I'm keeping it open in here. Okay, I'm calling it visit, okay, which returns type void. Of course, it can be anything. So visit can be any function, actually. The precondition for this function is just that the stack exists and it already initialized. It has some entries in there. And as a result of this, a postcondition, the function visit has been invoked for every entry in the stack, beginning from the entry on top of stack down to the very last entry in the stack. Okay, so I visit every one of these items and I perform visit, whatever visit does, and then after that I exit. So the size of the stack won't change as a result. However, the contents of the entries inside the stack will be changed according to visit. Okay, this is pretty much the basic functions that we could perform on a stack. Let's go now to the implementation, implementing the stacks on the computer using the C programming language. For simplicity and first way of thinking, we're going to implement the stacks using arrays. So in this kind of implementation, I'm going to assume that the stack, okay, is just a static array like this, okay, and it has as many items in here as the max could go, all right? And this is called S. So S is basically a pointer to an array of maximum size, okay? And when I push, then I'm going to be adding entries to here, all right? And when I pop, I will always take the very last entry in the array. Let's see. So here's the conceptual stack, all right? This container. And I always have this TOS pointing to the last entry. However, in real implementation, I'm going to implement it as an array of size 6, in this case, the maximum size I'm assuming, all right? And always, this is the stack S, a pointer S pointing to the beginning of the stack. However, when I push, I always add entries at location 0, location 1, 2, 3, and so forth. And this pointer actually is always pointing to the last full entry in this stack. So this is the top of my stack. So I always add, when I add, I increment this pointer to point to the next entry. And whenever I pop from the stack, this TOS is going to be decremented to go backward. Whenever all entries in here are filled with data, my stack is full. Whenever I don't have anything in the array, the stack is empty. So it's very basic and very simple. And for that, we're going to define this very basic data structure to define my stack and stack entries. In our case, in our example, I'm defining the maximum size of my stack, max stack, to be 6. And that's to go with the example I've shown on the previous slide. And the structure stack is actually contains 2 pointers, basically, 2 elements. Top, and that's basically going to refer to the top of stack, integer index. So top is this one, if you like. It's the pointer or the index of the last entry in the stack. And stack entry, okay, called entry, and this basically defines the stack, the array itself down here, okay? And I'm calling this stack with a capital S for just quick reference. Okay, based on this, let's implement these functions we just talked about in our prototypes. The first function was initialize the stack to be empty. As you remember, the precondition none, post condition, result of this, the stack has been initialized to be empty. Well, basically, create stack, it takes stack a pointer to the structure we just developed called S. And basically, all it does to initialize it is just make top of stack pointing here. And that means simply there are no entries in the stack. So it's pointing to entry number 0 in the stack. So basically, make is arrow top pointing to 0. And that's all it does. Okay? So very basic. Okay? And it's arrow in here minus greater because is of type pointer to a structure rather than a structure. So we're not using the dot operator, but rather we're using the arrow operator. Okay? Very simple function. Just make top stack pointing to the first entry, the 0 entry. Okay. Stack status, stack empty. Remember, this function has to check whether the stack in hand is empty or not. Return a true or false kind of thing. Well, very simple. The precondition stack exists and has been initialized, all right? And as a result, we're going to return a true false thing, a 0 or non-zero, okay? So it returns 1 if the stack is empty, otherwise it returns 0. All right, it's of type Boolean, stack empty, and it takes as input a pointer to my stack. All right, what do I return? Simply, if the top of stack equals 0, this is a condition, Boolean expression. Then if this expression is true, that means top of stack is pointing here. So return 1, and that means yes, the stack is empty. However, if I have entries in the stack, then the result of this expression is not going to be 1, but rather it's going to be false, because top of stack is pointing somewhere else. If that is the case, then return 0. And this, the result of this logical expression is going to be no, false, non-zero. Okay. The third function, and I think this is going to be the last function we're going to talk about in this lecture, and we're going to continue with others in the coming lectures. Stack full. Again, this is of type Boolean, and what I'm going to return, I'm going to check the stack, all right, to see if it's full or not. Again, the assumption is, and that's the precondition, is that the stack S already exists and it has been initialized. The return value, as a result, is of type Boolean, and it's going to return 1 if the stack is full, or 0 if the stack is not full. So basically, if top of stack is pointing here to the very last entry, that means that the stack is full, and I can't add more entries. Otherwise, it's not full. That means you can have more items to place in the stack. Okay? So it's very simple again. Boolean, stack full, the input is a pointer to the stack. And I want you to remember, this points to the whole structure of the stack. This is one pointer, and there's the top, which actually points to the last entry in the stack. And you have to distinguish between these two pointers. Okay, what do I return? I'm just going to make a check. Does top of stack point here? If it points here, that means the stack is full. Yes. So if stack arrow top equals to max stack, that's the maximum size of the stack, which is here. If that is the case, then yes, I'm full. So return true, return 1. Otherwise, if the top of stack does not equal to this, then the outcome of this expression is going to be 0, and that means the stack is not full. Okay? So that's pretty much what we want to cover and what we can cover in this class, as a matter of fact. Very basic. We're going to visit the rest of the functions in the coming class. To refer back to this class and more examples about this, you can definitely go to the internet, to the UNINETTUno site, click on the MedNetU link in there, and you're going to have a bunch of interesting stuff. Thank you very much. Bye.